Welcome back to our sequence on the engineering design cycle. This session focuses on creating a design specification. Before any engineering design can and should proceed beyond the idea stage to the design phase, a clear and precise specification must be defined to draw the line between success and potential failure. A design specification is essential to not only guide the selection of a design solution among many possible solutions, but also to ensure that the design team focuses on the performance and constraints of the design in a methodical and prioritized way. The design specification is almost entirely dependent on the application of the design. In this session, we'll look at some examples of design specifications and how they differ from complete product specifications. Specifications are a generic term and are used to describe the act of stating explicitly or in detail. In other words, a specification provides an explicit, concise, and clear description of a particular task or outcome. In the case of a design specification, this refers to the characteristics of a successful solution to the design problem. A design specification states explicitly and in detail what the goals of the design are, both in terms of performance and constraints. We separate design specifications into two groups for the purpose of the discussion here. The first are performance metrics. What does the design or product do, and how does it perform? What kind of accuracy does it offer? What kind of precision, dynamic range, response time, and so on. At the design phase, the specification should only list performance that is essential to the success of the design, and not venture into a wish list. The design specification also includes constraints, which are the limits in which the design delivers the performance metrics. The limitations may be a function of how the design is implemented, such as the power consumption or battery life. The constraints may involve conforming to certain standards, or adhering to certain size, weight, volume, or other dimensional restrictions. Just like performance metrics, however, design constraints must be met to ensure that a design or product has the best chance to be successful. Let's now take a closer look at the performance metrics associated with the design specification. These are the aspects of design performance that must be met in order for the design to be deemed successful. Which metrics and how they are quantified naturally depends on the specific design and its application to a product. While it may be tempting to list all desired performance metrics in the design specification, this list must be carefully filtered and separated into those metrics that are critical and those that are nice but not absolutely necessary to achieve. Performance metrics should be identified before choosing a design to avoid selecting metrics that just happen to coincide with certain components of the design. Metrics are a function of the application and should not be determined based on what's available off the shelf to use in the design solution. Listed here are just a few potential examples of performance metrics that may be used in a design specification for an airbag sensor system. For a safety system such as that used in an automobile, it is likely the detection limit will be a critical performance metric and therefore a part of the design specification. In such a system, we can imagine that if the sensor does not detect an acceleration at a low enough level or detection limit to protect the occupants of the vehicle, it is likely to be a sensor and a design failure. Thus, the detection limit will be included in the design specification at a level consistent with safety standards and product expectations in that sector. This is but one example of a necessary performance metric that should be included in a design specification. To further explore performance metrics, let's take a look at a product specification. This example is for an ocean optics spectrometer, but most technical products contain some sort of product specification in their documentation. The product specification gives us some clues about what the design specification might have been. In this case, since the whole purpose of the spectrometer is to detect color of light, it is likely that the designers cited a specific spectral or color range when generating the design specification for this line of spectrometers. In this way, product specifications give us an idea of the types of performance metrics we may choose to include in a design specification, both the nature of that metric as well as the units associated with the metric. On this slide, we see performance metrics associated with the design specification for a consumer device intended to detect the spoilage of milk in a milk carton using pressure. Note how simple and brief these metrics are compared to the complete product specification. The designers have limited their design specification to only 3 performance metrics that are critical to the success of the design. They have neither over or underspecified their performance, nor have they included more in the targeted performance than is absolutely necessary. Let's move on to take a closer look now at the constraints associated with the design specification. These are the aspects of the design that must be met in order for the design to fit into a particular product or application. Which constraints and how they are quantified naturally depends on the specific design and its application to a product. While it may be tempting to list all desired constraints in the design specification, this list must be carefully filtered and separated into those constraints that are critical and those that are nice but not absolutely necessary to achieve. Constraints, just like performance metrics, are a function of the application and should not be determined based on what's available off the shelf to use in the design solution. Listed here are just a few examples of constraints that may be applicable in engineering design. Some are dimensional, such as size, volume, and weight. Some involve power consumption and battery life. Others look at ergonomic and aesthetic constraints. Some address standards and other regulations, including safety, maintenance, and recycling. And there are many more possibilities of things that may constrain a design depending on where it will ultimately be used in a product and in society. While striving to understand appropriate constraints for a design specification, it may be necessary to look at similar or competing products to fully understand these constraints. As with metrics, however, it can be hard to tease out actual design constraints from a product specification. In this example, although many constraints are listed for system operation, it looks like the only one that was critical during the design process is the one constraining the overall power consumption of the sensor at about 350 milliwatts on the last line of the product specification. Existing product specifications can be useful in getting us in the ballpark of what our design constraints should be, but will also need to be grounded in other knowledge of the application of the design in order to make it into an actual design specification. On this slide, we see constraints associated with the design specification for a consumer device intended to detect the spoilage of milk using pressure. Note how simple and brief these constraints are compared to the constraints of the complete product that we saw on the previous slide. The designers have limited their design specification only to the constraints, including standards, that are critical to the success of the design. They have neither over or underreached their constraints, nor have they included more in the constraints than is absolutely necessary. In this slide, we take a look at another design specification, both performance metrics and constraints in their entirety. This device is intended to be worn on the head and to detect the presence of safety glasses worn in the proper position and on the head or in some other position that doesn't accomplish the safety goals of the glasses. Note again how concise and short the design specification is compared to product specifications. These are the critical parameters we must meet for a successful design. No more and no less. The product specification, on the other hand, is much more complex, shown here in another example for a photodiode or light sensor. The product specification will involve a much wider range of tests and characterization efforts than the initial design, and in the end it may be difficult to tease out the design specifications from the entire product specification. But these product specifications do provide some guidance for what we should consider when generating the design specification within a particular category of designs or products. Oftentimes, when laying out a design specification, it can be helpful to look at product comparisons that are already available on the World Wide Web or through other sources. In this example, 3 different types of digital cameras are compared, providing great insight into what the critical performance metrics are. In this case, the image ratio, image resolution, and total number of pixels appear to be the most important to the customer. And if we are designing a similar product, should be important to us as designers as well. In this session, we have completed a brief overview of the design specification and its purpose in the design solutions phase of the engineering design cycle. In combination with the possibilities we have identified and documented in this phase of the design cycle, we are now ready to move on to selecting the best solution and moving forward in the engineering design cycle. Thank you for joining us. We certainly hope that this session has been helpful in creating your own design specification, and that you'll join us again as we take a detailed look at other phases of the design cycle.